Hello everybody, you are welcome. Today we will solve paper 6, variant 1, October-November 24, Chemistry IGCSE. First question, a student has a mixture of copper 2 carbonate powder and crystals of sodium sulfate. Copper 2 carbonate is insoluble in water, while sodium sulfate is soluble in water. The student tries to obtain pure copper 2 carbonate and crystals of pure sodium sulfate from the mixture. Figure 1.1 shows the steps the students carries out. Step 1. Add distilled water to the mixture and stir. Step 2. Filter the mixture to separate residue from filtrate. Okay, by using filter paper and funnel. Step 3. Heat the filtrate from step 2 until crystals start to form. Step 4. Leave the residue on the filter paper from step 2 in warm place to dry. Here in this question, the student tries to separate one salt from another in container containing a mixture of them. How come? By using water. So it depends on the solubility of both degree of solubility of both salts. One of them insoluble, copper 2 carbonate, and the other one is soluble, sodium sulfate. Mainly we depend on filtration process. The steps for filtration and how to obtain or separate both salts from each other. Letter A. State what happens to the sodium sulfate in step 1. Sodium sulfate, as indicated in the question, is soluble, so it dissolves in water. Sodium sulfate dissolves in water. Letter B. State what is removed from the filtrate in step 3. In step 3, the student uses the filtrate and heat it up in evaporation dish. So what would happen at or during heating? Water vapor is released, so water evaporates from the basin or evaporation dish by evaporation. Water is removed by evaporation. Letter C. Describe what must be done after the filtrate has been heated in step 3 to obtain larger amount of sodium sulfate crystals. To obtain larger amount of sodium sulfate crystals allows the solution here to be crystallized. How come? By cooling down. Okay, cooling slowly. Here leaves the solution to cool slowly. Okay. Letter D. Single I. State what must be done in the residue before it is allowed to dry in step 4 to obtain pure copper 2 carbonate. Copper 2 carbonate is insoluble. It is residue now. Okay, it's separated as residue. How to obtain pure sample of copper 2 carbonate? How? By washing the residue by distilled water. Okay, wash with distilled water. Okay, using the squeezing bottle with distilled water. Okay, double I. During washing, what would happen to the residue? Any impurities, any ions, any ions of filtrate found in filtrate, like sodium ions or sulfate ions, will be washed from residue down and reach the filtrate. So identify the substance removed from copper 2 carbonate in D single I, sodium sulfate ions. Okay. Now for question number 2. A student investigates the reaction between aqueous magnesium sulfate and aqueous barium nitrate. A precipitate of barium sulfate forms in the reaction. The student does 8 experiments. Look at this experiment from beginning. The reaction depends on aqueous magnesium sulfate, this colorless solution, and aqueous barium nitrate, also colorless solution. When we add both of them together, we obtain a precipitate, white precipitate of barium sulfate. Okay, look at the experiment here. When we add both solution together, immediate white precipitate of barium sulfate is formed. Okay, yes. Now also the same magnesium sulfate solution, we dispense drops of barium nitrate or any salt of barium chloride, barium nitrate. Okay, will allow immediate precipitate of barium sulfate formed at once. Okay, now experiment 1. Fill purette. This purette with aqueous magnesium sulfate. Run some of the aqueous magnesium sulfate out of purette by this tip. Okay, this step. Run some of the aqueous magnesium sulfate out of the purette so that the level of aqueous magnesium sulfate is on this purette scale. Purette scale, I mean here reach 0, starting from 0. Okay, now fill second purette with aqueous barium nitrate, one of magnesium sulfate and another purette for barium nitrate. Run some of the aqueous barium nitrate out of the purette so that the level of aqueous barium nitrate is on the purette scale, I mean from top at 0. The student add 4 cubic centimeter of aqueous magnesium sulfate from the first purette into 10 cubic centimeter measuring cylinder. Okay, the student take measuring cylinder of maximum volume of 10 cubic centimeter empty. Okay, with maximum volume 10, he add 4 cubic centimeter of aqueous magnesium sulfate. Then add from another purette, add 1 cubic centimeter aqueous barium nitrate from the second purette into the same measuring cylinder. Okay, place stopper on the top of the measuring cylinder and invert the measuring cylinder several times, stopper or lid to close it. Leave the measuring cylinder to stand for 15 minutes. Record the level of precipitate on the measuring cylinder. Okay, rinse the measuring cylinder with distilled water. This is the first experiment. Then now the student use what? The student use experiment 2, 3, 4 up to experiment 8. In each time he changed the amount or volume of aqueous barium nitrate. Okay, but take or took the same volume of magnesium sulfate, So here he changed 1.5 of aqueous barium nitrate instead of 1, 2.5 instead of 1, and so on till reaching 5.5 instead of 1. So the independent variable in this experiment, barium nitrate solution. Okay, the volume of barium nitrate solution. Now look, use the information in the description of the experiments and the measuring cylinder diagrams to complete table 2.1. The volume of aqueous magnesium sulfate is the same in the 8th experiment, so he used 4 for what? 4 cubic centimeter of magnesium sulfate in each experiment. Okay, while in for barium nitrate purette he used 1. Okay, then change it into 1.5, 2.5, 3.3, 3.5, 4.5, 5, and then 5.5. Okay, depending on the data provided in the question. Now he asked me to observe and record the reading of precipitate, the volume of precipitate formed in each experiment. Here 1.2, yes, 1.2, right. Here 1.8, right. 3, 3.6, right? 4.2, 4.6, 4.6, 4.6. Okay. Now for letter B. Letter B, complete the suitable scale on the y-axis and plot the result from experiment 1 to 8 on figure 2.1. Draw two straight lines of best fit through your points. The first straight lines should be for the first 5 experiments and they must be extended to path through 0 and 0. The second straight line should be for the last 3 experiments and they must be horizontal. Extend the straight lines so that they cross each other. Okay, here for x-axis log, he plot volume of aqueous barium nitrate on x-axis y because the student changes the volume of aqueous barium nitrate in each experiment. He used 1, then 1.5, then 2, and so on. So the variable that changed by examiner or by the student or researcher is called independent variable. Independent variable must be placed and plotted on x-axis independent. What about the volume or the level of precipitate? It depends on the amount taken from barium nitrate in each experiment. So it is considered dependent variable. Dependent variable. Okay, must be plotted on the y-axis. Here y-axis not scaled. We have to scale it before plotting the data. Look at this small table from the previous results. Okay, when the student use barium nitrate with 1, okay, he obtained volume of precipitate equal 1.2. So before plotting we have to scale y-axis. Here the number of small squares like this equal 50 on the y-axis. We can divide the scale into 5. How come? Each 10 small squares use 1. So here 1, 2, 3, 4 and 5. Okay, each small square with 0.1, each 10 equal 1. Now plot the data provided in the table. 1 and 1.2, yes, 1.2, 1.5, 1.8, yes, 2.5, 3, okay, 3, 3.6, yes, 3.5, 4.2, yes, 4.5, 4.6, 5, 4.6, 5.5, 4.6, 8 dots or small crosses or small circles. Okay, now one line of best fit, it doesn't matter to path in all the points in between, yes, okay, but with equal number on both sides, up and down of this line, straight line. Here line of best fit extended of what? Extended to 0 and 0 according to the question. He asked me to extend, okay, but please don't extend without permission or without asking in your exam. Okay, must plot the exact data provided, not extrapolation or extension of your lines. If he not asked you to extend, please don't extend your lines. Okay, now for the other last three experiment, number 6, 7 and 8, look, another line. They are crossed at each other here in this point. Extend the straight line so that they cross each other. We finish this question for 5 marks. Yes, right, good. For letter C, figure Use figure 2.1 to deduce the level of precipitate on the measuring cylinder scale when the experiment is repeated using 2.8 cubic centimeter of aqueous barium nitrate. Show clearly on figure 2.1 how you worked out your answer. Look please to this figure. Okay, the same like in B. Okay, plotting data cross together. Yes. Now the question: when the student used 2.8 of aqueous barium nitrate, how we obtain the result of precipitate, the level of precipitate? Look, 2.8 here. We have, by using your ruler, to draw this line up to touch the graph, and then horizontally to touch the y-axis. Read the y-axis now, 3.4. So level of precipitate when the student use 2.8 cubic centimeter of aqueous barium nitrate, we obtain 3.4 cubic centimeter of precipitate. It's okay. 3.4. For letter D, the student repeats the experiment using 6.5 cubic centimeter of aqueous barium nitrate. Predict the level of precipitate on the measuring cylinder scale. Explain your answer. Predict and explain for 2 marks. Now, look. When the student used 4.5, it reached 4.6 precipitate. Okay, cubic centimeter of precipitate. When increased into 5 cubic centimeter of barium nitrate, also still the volume of filtrate the same, 4.6. At experiment number 8, he used 5.5. Also, we reached 4.6 cubic centimeter of filtrate. Now predict, what about when we using 6.5 cubic centimeter of aqueous barium nitrate? Yes, the same. We obtain 4.6 cubic centimeter. What is the reason? The reason, all magnesium sulfate has been reacted at which point? From here. Okay? From here. Here magnesium sulfate considered what? Considered limiting reagent. Okay? So no further increase in precipitate volume. Okay? All magnesium sulfate has run out, has reacted, so no further increase in precipitate as limiting. It acts as limiting reagent or limiting factor. Now for letter E, sketch on figure 2.1 the graph obtained if all of the experiment are repeated using aqueous barium nitrate of half the concentration used in experiment 1 to 8. Look as a graph. Okay, here for original 8 points. Okay, now what will be happened? Okay, when we using barium nitrate of half the concentration used, half the concentration, not the volume is the same, but what about the concentration of barium nitrate decreased or reduced into half? So predict or sketch the graph obtained. Yes, of sure, as the concentration of barium nitrate is reduced into half, so the volume of precipitate will be also reduced into half. Look, into half. Here must be shift to right, okay, and down, and the volume, maximum volume obtained here in this last 3 points nearly equals the half of maximum concentration. Here we reached, 4.6. Here about 2.3. Okay, about 2.3 nearly in this line. Okay, yes. Now for letter F, suggest why the measuring cylinder is inverted several times after the aqueous barium nitrate is added. Just we add barium nitrate into magnesium sulfate, the precipitate will be formed at once, but in irregular manner. So why we invert the measuring cylinder containing both solutions? Yes, to what? For mixing solution evenly, to mix the solutions evenly. Okay, then what about G? Suggest why the measuring cylinder is left to stand before the level of precipitate is recorded. Before recording the data, we have to left the measuring cylinder for 15 minutes. Why for 15 minutes? To allow settling of precipitate down, to allow the precipitate to settle down at the bottom of measuring cylinder. Yes, here irregular. Look, this irregular precipitate, we have to wait for about 15 minutes like in this exam. Why? To allow all the precipitate as white precipitate to settle down at the bottom. Okay, now for letter H, the volume of both aqueous solutions are measured using pirettes. The student used two pirettes, one for magnesium sulfate and the other one for barium nitrate. Give a reason why pirettes are used rather than the measuring cylinders. Why? Pirettes like this, measuring cylinder like this. Pirettes are more accurate, okay, than using measuring cylinder, more accurate. Now for suggest why pirettes are used rather than volumetric pipettes, and why we not use volumetric pipettes. What's the shape of volumetric pipette? Do you know? Here this pipette, yes, right. Here volumetric pipette. Volumetric pipette, we use it in lab when dispense fixed volume of solution. Look at this mark. Yes, mark sign. This indicate 25 ml of solution taken. Fixed, just only fixed. But in this exam, the student use several and different volumes of barium nitrate in each experiment. 1, 1.5, 2, 2.5, and so on. How come? How we can use by this volumetric pipette? We can't. Okay, so the answer here, pirettes allow different volumes to be measured, while for volumetric pipette measure fixed volume in each time. Question number 3. A student tests two solids, solid T and solid U. Test on solid T. Solid T is lithium sulfite. Complete the expected observations. Letter A. The student carries out a flame test on solid T. Observations. What's the sample of lithium sulfite? Li2SO3, containing two types of ions, containing cations and anions. Cation like lithium Li plus 1 and sulfite SO3 minus 2. Okay, now in this question we asked to make observations on certain experiments to detect the presence of lithium and sulfite. For lithium we use flame test used to detect the cations, okay, like metals like copper Cu plus 2, Fe plus 2, Fe plus 3, and so on, aluminium, sodium. Here for lithium, if the salt contains lithium, what's the color of the flame? Look at the experiment. Here the Bunsen burner containing two parts of flame, non-luminous outside, outer non-luminous flame, and inner luminous. We subject a wire containing sample of salt into the outer or external layer, external flame. Look at the experiment. if this loop of wire containing lithium sample, lithium salt, what's the color of the flame of non-luminous part? Bunsen burner flamed with red color, red flame. Okay, so the answer red flame. Now for letter B. Letter B ask about anion sulfide. Sulfide detected by adding acidified aqueous potassium manganate. Sulfide is source of sulfur dioxide, SO2. Sulfur dioxide reduces KMNO4 with purple color into colorless like this. Potassium manganate 7, KMNO4, containing source or mixed with source of SO2, I mean sulfide. If SO2 evolved as gas, it decolorizes the potassium manganate. Look, this purple color disappear when passing SO2 within. Okay, so the answer now from purple into colorless. Okay, now for letter C, single I, to the second portion of solution T. The student adds excess dilute nitric acid. Okay, T, second portion of T, the student adds excess dilute nitric acid. The gas produced turns filter paper soaked in acidified aqueous potassium manganate 7 white. Okay, acidified aqueous potassium manganate 7 white, turns from purple into white. Identify the gas produced. I said before, this SO2 gas, sulfur dioxide. It decolorizes the color of potassium manganate from purple into colorless, or potassium dichromate from orange into colorless also. Okay, now look at this experiment here. Test tube containing acidified mixture of lithium sulfide. Sulfide is source of SO2. When heated up, acidified firstly with dilute nitric acid or dilute hydrochloric acid, whatever, okay, and warmed over flame, what would happen? SO2 gas released. This gas decolorizes the filter paper soaked in potassium manganate or permanganate, potassium manganate 7, or even potassium dichromate with orange color into colorless also. Okay, to the solution produced in CI, the student as equals barium nitrate. Observations, okay, lithium sulfide and barium nitrate. What would happen? Double exchange, double displacement, lithium nitrate and barium sulfide. All the four compounds here, okay, are colorless. So no change, no gas released, no precipitate is formed, no change happens. Okay, so no change. Now for test on solid U, we have finished completely solid T. Solid T was lithium sulfide. Okay, we detect the presence of lithium by flame test, and we detect the presence of sulfide by potassium manganate solution, acidified potassium manganate solution. It decolorized and changed from purple into colorless. Now with another solid U. Solid U contains one cation and one anion. 1 and 1. Table 3.1 shows the test and the student's observation for solid U. The student dissolves solid U in distilled water to form solution U. The student then divides solution U into 3 portions. Portion 1. To the first portion of solution U, add a few drops of aqueous ammonia, the observation green precipitate. When we add ammonia to certain solution and the green precipitate is formed, this indicates presence of either one of the 2 cations. Here he asked me about 2 cations, identify 2 cations that the test and observation in table 3.1 show could be in solid U. Either iron 2 Fe plus 2 or chromium 3 Cr plus 3. Now for indicate this green color, look, test for iron 2 sulfate containing iron 2 ion Fe plus 2 and ammonia solution. Okay, look, adding a few drops of ammonia to sample solution of iron 2 sulfate. Green precipitate is formed. It's okay. What about for this part? For chromium, also small amount of ammonia added to chromium chloride, for example, any salt containing chromium, what would happen? Green precipitate is formed also. Okay, both with ammonia form green precipitate. Now look, test on solid U. Solid U contains one cation and one anion. Table 3.1 shows the test and the student's observation for solid U. The student dissolves solid U in distilled water to form solution U. The student then divides solution U into 3 portions. For portion 1, the student add to the first portion of solution, the student add a few drops of aqueous ammonia. The observation green precipitate is formed. Ammonia is used to detect cations and forms green precipitate when the solution contains iron 2 ions Fe plus 2 or chromium 3 ions. Look at the question now. Identify 2 cations that the tests and observation in table 3.1 show could be in solid U. Yes, I mentioned or I said iron 2 Fe plus 2 or chromium 3 Cr plus 3. Now to check by this experiment, look at this video. For iron 2, here iron 2 sulfate, source of iron 2 ions Fe plus 2. We test by using ammonia solution. Add drop by drop, few drops of ammonia to solution containing iron 2. What would happen? Yes, green precipitate is formed at once. Yes, good. What about for chromium? When we add ammonia solution to salt or solution containing chromium, like chromium chloride for example, what would happen? Dirty green precipitate is formed at once. He asked how to confirm which one is present, N, D. The test used barrel 2 ammonia solution is using sodium hydroxide, excess sodium hydroxide, aqueous sodium hydroxide. Add excess aqueous sodium hydroxide. That's the name of the test. Cation. For look firstly, okay, for this one, if chromium 3 is present, what would happen to green precipitate? Green solution is formed. Sodium hydroxide with chromium ions, it forms precipitate at once. If we add excess of sodium hydroxide, what would happen to precipitate? It dissolve and form a green solution. While if the solution contains iron 2, what would happen? Look at the video now. Okay, iron 2, if green precipitate remains, okay, or forms, then turn into brown, this indicate presence of iron 2. Look at the second part of this video. Here for ammonia, okay, what would happen after shaking? It dissolve. Okay, this test for ammonia, dispersion or dissolve. While in second test, when using sodium hydroxide for iron 2, green precipitate is formed and still and remains when we add excess of sodium hydroxide. This indicate presence of iron 2. Okay, here dropwise, then dirty green precipitate forms when we add excess sodium hydroxide. What would happen? Look, okay, now add sodium hydroxide, excess sodium hydroxide. What would happen? Look, remains, the precipitate remains, okay, insoluble. This indicate presence of iron 2 ions. Here for cation detection, what about anion? Anion with negative charge to indicate and to know the identity of solid U. Okay, that's for cation. What about for anion? For anion, test 2. To the second portion of solution U, we add 1 cubic centimeter of dilute nitric acid followed by few drops of aqueous silver nitrate. We use silver nitrate to detect the presence of halogens. I mean chloride ion, fluoride, chloride, bromide, iodide. Okay, all of these halides we can check their presence by using acidified aqueous silver nitrate. Okay, if yellow precipitate is formed, this indicate what? Look, identify the anion in solid U. Right here, unknown halide, chloride, bromide, iodide solution dissolved in dilute nitric acid. This unknown acidified salt. We add silver nitrate solution. Look, a silver nitrate solution dropwise. Here precipitate is formed of silver halide, silver chloride, silver bromide, silver iodide, and the color of precipitate indicate the presence or the identity of this halogen. Look now for this one. Test for halogens, acidified silver nitrate AgNO3. If chloride present, white precipitate is formed. If bromide present, cream precipitate from AgBr is formed. For iodide, yellow precipitate is formed. So we detect, we confirm now the identity of this anion as what? As iodide. Okay, as iodide. Look, acidified silver nitrate test, very pale yellow precipitate AgI is formed. Okay, now for this part, what about test 3? To the third portion of solution U, add 1 cubic centimeter of aqueous chlorine. The solution turns brown. To third portion of U that containing iodide, add 1 cubic centimeter of aqueous chlorine. What's the relation between chlorine and iodine or iodide? Look please, here potassium iodide, any source of iodide, any source, okay, like potassium iodide. It contains iodide ions, okay, iodide ions, I-1. What if we bubbling chlorine gas inside potassium iodide? What would happen? Chlorine, as you know, precedes above iodine, so it can replaces or displace iodine from its salts, okay, so releases iodine in brown color, so the solution turns brown. This indicate and confirm that U contains an anion called iodide. It's okay here by displacement reaction with chlorine. Now for last question about beetroot. Number 4, beetroot is colored vegetable. The color is caused by mixture of water-soluble colored compounds. Plan an experiment to find how many water-soluble colored compounds there are in beetroot. Include in your plan, in your investigation, in your plan to do this experiment, how to extract the colored compounds from beetroot. How? We have to answer this 3 bullets. How to separate the mixture of colored compounds. How the results show how many colored compounds there are in beetroot. You are provided with beetroot, 1 piece, for example, distilled water, and common laboratory apparatus. Okay? Look now, with 6 marks. First one, steps to extract the colored compounds. How to extract? So the steps to extract colored compound. We have piece of beetroot. Look, crush, grind beetroot. How? By using pestle and mortar. Pestle and mortar. Then we add water to form solution. Use pestle and mortar. Okay, mix with water to form solution. Then second question, how to separate the mixture? Steps to separate the mixture. How? Firstly, apply extract onto chromatography paper. Point of origin. Okay, we place 1 drop of this extract on chromatogram. Okay, chromatogram paper like this, and place the chromatogram paper dispense in solvent. Here the solvent is water because beetroot colors mixture of water soluble color compounds. So the solvent is water, but the baseline must be above the level of solvent. And drawn by pencil, not by pen. Okay, then place and hold the paper from above and cover the container with lead. Look, use chromatography technique. This technique, then place paper in solvent, water immersed in its step in the solvent, which is water here in this example. Last question here, how the results show how many colored compounds there are in beetroot. Look, count each spot on the chromatogram represent different compounds. So we have to count the number of spots to determine the number of water soluble colored compounds in beetroot solution. It's okay, and we need also to detect their RF value. Okay, RF value, as you know, from the rule RF equal the distance moved by each pigment, for example, a red pigment, for example, over the distance moved by solvent. Here 2 over 10 equal 0.2, and RF, as you know, must be less than 1. Okay, must be less. Its value must range from more than 0 and less than 1. It's okay. Okay. Thank you. See you next time, inshallah. Bye bye.